Alrighty folks, I have a doozer for you today. We have to try and cram 75 minutes of a lesson into a 15-minute video. So here we go, and bear with me as I teach you applications of derivatives in trigonometric functions. And the application type we're going to do today is oscillation. But before we do that, recall, if you have a function of sine of x, the derivative is cos x, meaning that the instantaneous rates of change along your sine x is a function of cos x. Similarly, a function of cos of x has a derivative of negative sine x, meaning that the instantaneous rates of change of cos x is a function of negative sine x. So let's begin. On page 241, number 5. The question says, a marble is placed on the end of a horizontal oscillating spring. If you ignore the effect of friction and treat the situation as an instance of simple harmonic motion, the horizontal position of the marble as a function of time is given by the function h at t is equal to a cos 2 pi ft, where a is the maximum displacement from rest position in centimeters, f is the frequency in hertz, and t is time in seconds. In the given situation, the spring oscillates every 1 second and has a maximum displacement of 10 centimeters. So, let's just understand the question. This ball oscillates 1 full cycle every 1 second. It reaches 10 centimeters as a maximum displacement from the center, and it continues to oscillate in a cosine function. Okay, so let's begin with A. The A says, what is the frequency of the oscillating spring? Well, frequency is just the number of cycles or revolutions or oscillations per second. And because in the question it states that it completes 1 oscillation every 1 second, that tells us 1 cycle per 1 second. The frequency is equal to 1 hertz. That is one simple bread and butter mark. And let's move on to B. Write the simplified equation that expresses the position of the marble as a function of time. Well, all we have to do is just create a standard equation. So let's begin with the standard equation which they give us. A, the maximum displacement from the center in centimeters, cos, the function, 2 pi f t. What is 2 pi f? We have never seen this before. Okay? But for those physics students out there, f, as we know, is equal to 1 over t, or the period. And we know that our b value is 2 pi over the period. So with some substitution, you can find out that b is equal to 2 pi f. So in simpler terms, this 2 pi f is simply just our b value. But we don't really care about our b value. In fact, if we know our f, and if we know that 2 pi is just 2 pi, then we can actually simplify as 2 pi. Okay? So now we'll just include all of the variables for what they are. In the question, A is the distance from the center is 10 centimeters. So, in blue, I'm going to write h at t is equal to 10 cos of 2 pi, f is 1, t. That is another easy one bread and butter mark. So now let's move on to C, where C, we are dealing with the derivative. Determine a function that expresses the velocity of the marble as a function of time. So let's begin. C, from previous units, s of t, or position, when you take the derivative of it, it becomes v of t, or s prime t. This is just the instantaneous rate of change of displacement. And we know that the instantaneous rate of change of displacement is actually the velocity. So if we want to find a function that represents the instantaneous rates of change of position, or the velocity of it, then all we have to do is just take the derivative. So what we're going to do is we're going to begin with our h at t is equal to 10 cos of bracket 2 pi t. And we're going to begin to differentiate. So let's recall over here. So if our function is cos x, the derivative is negative sine x. So what we're going to have to do is differentiate this in terms of negative sine x. So let's begin. H prime t, or the velocity of time, is equal to 10, which is just our amplitude, right, multiplied by the derivative of cos, which is going to be negative sine of 2 pi t, times whatever's inside that bracket, which the derivative is just 2 pi. Now all we have to do is simplify. Negative 20 pi sine 2 pi t. Once again, another simple bread and butter mark. And now let's move on to D, where we deal with the second derivative. Determine the function that expresses the acceleration of the marble as a function of time. Acceleration is the derivative of velocity, where acceleration is the change in velocity over a frame of time. So let's begin. We can be taking either the second derivative of our first function or the derivative of our velocity function. For the sake of it, because we already did those steps, I'm going to begin with my derivative function. H prime t is equal to negative 20 pi sine of 2 pi t. And if we want the second derivative, we are just going to be differentiating this function. So let's recall over here again. When we have a function of sine, the instantaneous rate of change of sine is a function of cos. So we're going to have h double prime t is equal to, we're going to start with our a value, negative 20 pi, times the derivative of sine, which we agree is cos of 2 pi t, times whatever is inside that inner bracket, which is 2 pi. Finally, we can then simplify this equation to determine h double prime t is equal to negative 40 pi squared cos of 2 pi t. And there we have it. Bread and butter mark number 4. Congratulations, and thank you very much for watching.